So, question 20, and we've got a little bit of vector work to do at the beginning here. Let's have a look. So we've got a square OACB, where O is the origin. The position vectors for AB are defined as that. So OA is little a and OB is vector B. PQ, R, and S are basically set in proportion, the story goes here. OP is KA, so this bit is KA, which means that the bit from A to P, on account that K is somewhere between 0 and 1, must be 1 minus K. And then what else are we told? That AQ is KB, and RC is KA, and SB is KB. Therefore, they're all positioned. So here's our basic diagram now. Let's find the question. Where are we here? So here we go. Using vector methods, prove that the size of angle PQR is 90 degrees. Now, this is always a dead giveaway, the fact that we're going to have to do a dot product. So angle PQR, this little angle up in here, we obviously need a vector for PQ, one for QR, and show that the dot product is 0. So here we go, PQ. So a vector from P to Q is PA plus AQ. So we'll let the examiners know that's where it's coming from. And then we'll simply add together what we were told. So PA is this part, 1 minus K, lots of A, and AQ is KB. So that's the first step. And then we want a vector QR, so exactly the same way. Q to R is Q to C plus C to R. And Q to C is 1 minus KB. And C to R is in the negative direction, so it'll be negative KA. Right, so once we've got those two vectors, then we've just basically got to do the dot product and show that it comes out as 0. So here we go. I've copied the two lines we just did down to here. And then off we go with the dot product. So we're doing the dot product of this with the second expression. So here it is. And then we actually need to start expanding it out. So we're going to get a 1 minus K squared A dot B minus a K 1 minus K A dot A from the first and the last terms. Then from the middle inside pair, we're going to get a K 1 minus K B dot B. And from the last two terms, we're going to get a K squared B dot A. And now, because in the whole initial beginning we were told the outside shape was a square and A and B then are perpendicular, we know that A dot B is 0, but we've got to let the examiner know that, so we need to write it down. So therefore our dot product from here will simplify. The terms with an A dot B here and here are going to disappear. We're also using the fact that A dot A is the magnitude of A squared and B dot B is the magnitude of B squared. So what's left is we've got a minus K squared magnitude A squared plus a K minus K squared magnitude B squared. And we may as well factor out the K minus K squared here. So if we take this term first, then we've got K minus K squared magnitude B minus magnitude A squared. And then we make the observation that since it's a square, the magnitude of A is equal to the magnitude of B. Therefore, this term must be 0. Obviously, this term could be if K was 0 or 1, but then we're basically just looking at the original square. So that kind of case is covered. So we've shown that PQ.QR is 0. Technically, we should always state that so long as these two aren't 0, which we know they're not, but we'd still make that point that the magnitude, because obviously if one of these was a 0 length vector, the dot product would be a 0 length vector. So because these two are not 0 and P.Q is equal to 0, then the angle must be 90. So fairly slow going. We've probably used up all the 5 marks, but let's hope things speed up over the page. So here we go. And over the page, we've got 4 marks. What's going on here? Suppose that in square OACB, it is known that OA is 10, and so it's basically the same picture. We've just got now, we've animated the diagram. P is moving away from O at the speed of 0.2 centimeters per second, and X is the distance OP. So basically, we have to find the rate at which the area of the square is changing. So Those of you who've done this before will spot here's a rate we're given, here's the rate that we are after, so it's a related rate problem. Let's go. So we'll say A is the area of PQRS, and given this rate dx dt, because x was OP and P is moving away from the origin at 0.2, we have to determine dA dt when x is equal to 3. So we need an expression for the area. My way of doing it here, there are lots of different ways of doing it, is basically to say the area of the outside square is 10 squared, which is 100. And from that, we need to subtract 4 little triangles. OP is x, the base is 10 minus x, and then we need to halve it all. So it'll be half of x times 10 minus x, and then we've got 4 of them. And then we basically expand this out, which is fairly trivial, and we end up with 100 minus 20x plus 2x squared. So now we're ready to get dA dt, so I'm implicitly differentiating here with respect to time. So the 10 squared's gone. We differentiate the minus 20 to get minus 20 dx dt, and this term will give us a 4x dx dt. Now, we know dx dt is 0.2 and we know x is 3, so basically to get dA dt we just substitute all that lot in. Negative 20 lots of 0.2 plus 4 times 3 times 0.2, and we end up with negative 1.6. So that's the rate at which it's changing. So this part was a lot quicker than part A, and I'm guessing students might have chosen to skip part A because A, it's a proof, and B, it looked like it would take a long time.